Welcome back, everyone. So let's talk a little bit about this experiment that you see in front of you that was done first by Professor Hertz. Hopefully that name is, or that word is familiar to you as a unit of frequency. But let's talk about this experiment that is generally known as the photoelectric effect, what it is and what it tells us. So in this experiment that was actually done with several different metals, what was determined was that when a particular metal is exposed to light of a particular frequency, that those metals actually release or eject electrons, that subatomic particle from the atom, that metal ejects electrons when the light strikes their surface. Now, how those electrons are detected, you talk about in other classes. But from this experiment that was done with several different kinds of metals with light of particular frequency and wavelength, it was determined that the electron has not only particle-like tendencies, but also that the light that travels has a particular energy called photons, and the energy is related to the wavelength of that light. And so we can take that observation, which is what Hertz and specifically Max Planck did, took that observation and was able to derive an equation that related the energy of a light with regards to its frequency. And that relationship that you do need to memorize, because I've got the star by it, is that the energy of a particular light wave is equal to its frequency times a constant, which, named after Max Planck, is given Planck's constant. I will give you this constant on the exam. It has units of joule times seconds. So that's one thing that you need to know this you need to know this relationship that came from the photoelectric effect experiment. And you should also know this term of photon. What exactly does photon mean? Photon is essentially a chunk of energy that is associated with a particular light wave. And so from this equation from Max Planck and from the photoelectric effect, it was deduced that a photon is a particular packet of energy that can have a particular value. And that value of energy, that value of energy associated with the photon can be calculated from this equation with regards to energy and frequency. So let's go ahead and let's do a calculation with it. Let's say I was to ask you the energy of one photon, of one pocket of energy associated with light that has a particular wavelength. We used this wavelength in the previous video as an example. We want to calculate the energy associated with that wavelength of light for one photon. Well, as we just said, the energy of a photon is equal to Planck's constant times frequency. I have wavelength, but I calculated the frequency of that wavelength in the previous video, which was 5.09 times 10 to the 14th hertz, or seconds per one. And so taking that and multiplying by the appropriate Planck's constant, I get an answer in joules. So that is the amount of energy that is associated with one photon, one packet of energy of light at this particular wavelength. And you may think, okay, that's great. It's only one photon though. What if when we deal with elements Many times we deal on a mole basis. How much would 1 mole, what if I have a whole mole of photons? Like 6.022 times 10 to the 23rd of them. Well, I can still use my energy that I have calculated here, realizing that that energy is just for 1 photon. I can then multiply it by Avogadro's number to get me an answer in joules per mole, because I want to know the energy, and for this question I want to know the energy associated with a mole of photons. And so doing that gives me an answer of 2.03 times 10 to the 5th joules for every mole of photons that have a wavelength of this particular nanometers. So you should feel comfortable being able to use this equation that relates energy and frequency along with the equation that relates frequency and energy to solve math problems with regards to electromagnetic radiation.